Thank you for inviting me to give this talk, and thank you to Sivan Barbu and Judith Hubbard, who are my advisors and co-authors. We're slightly shifting gears now, talking about large scales, faulting and folding. Faults and folds are geologic expressions of plate tectonic activity. They accommodate the tectonic forces that drive the growth of topography on the surface. So it's very important to understand both the structure and behavior of faults and folds, because they play a very important role in trapping oil, creating minerals of economic value, generating natural catastrophes, earthquakes, landslides, tsunamis, and so an in-depth understanding of faulting and folding can help us understand the complex crustal deformation processes that build and maintain this ever-evolving system. So the main motivation for my talk today is about bringing structural geology and fault dynamics together. Kinematic models have been used for decades now of faults and folds, and they trace the evolution of deformation over geological timescales. But we need to understand how the structural and geometric features influence long-term mountain building processes and short-term seismic cycle processes. Fault-related folding, and especially fault-bend-fold theory, is widely used to construct both regional and balanced cross-sections in areas of active compressive deformation. And they're also commonly used as a tectonic model when calibrating slip or erosion rates from geomorphic indicators or active faults. And they've also been very widely used to simulate the evolution of structures that are growing by king-fan migration in the upper crust. To briefly describe the basic concept of fault-bend-fold theory, let's first consider a hypothetical case of a fault in cross-section with one bend joining an upper and lower segment. So if you consider rigid block translation of the hanging wall parallel to the upper segment, you'll create a void between the two fault blocks, whereas translation of the hanging wall parallel to the lower segment produces an overlap. Now, we know both of these cases are sort of unreasonable. So what actually happens is folding of the hanging wall block through the development of these kink fans accommodates fault slip without creating any unreasonable overlap or void. And evidence of these kind of fault bend folds are seen both in the field as well as in seismic reflection profiles. So in our study, we developed a new geophysical framework that combines these geology-based models with physics-based earthquake cycle models. So we basically apply fault bend fold theory to rate and state friction faults, so we can have a unified representation of both fault slip and inelastic strain along these fold axes, which accommodates the off-fault deformation. And using this framework, we conduct a parameter space study to explore the dynamics that emerge out of a simple fault bend fold system. So we here use a synclinal fault bend fold. It's a single fault with two segments, an upper segment which dips at 40 degrees and a lower segment that dips from 30 to 0 degrees. And we include an axial surface that extends from the surface to the fault bend, and this axial surface represents the fold axis that bisects the angle between the two fold limbs, and this is where strain is localized during folding. And we vary the shape of the fold, as you can see here, by varying the angle between the two fault segments, and as you can see, the bend gets sharper as you move towards the right. To capture the fault dynamics of fault bend folds over multiple seismic cycles, we adopt the multiplicative form of the rate and state friction framework. The red regions here are the velocity weakening regions, and the black is the velocity strengthening region. And for the rheological properties of axial surface, since we don't know much about that, we basically assume an overall velocity strengthening behavior, so sort of approximating it for a viscoelastoplastic material. And we also explored the frictional parameters. The one that we use here is the non-dimensional parameter, which we call here RU, the ratio of seismogenic width and critical nucleation size. Here is an example of how seismic cycle complexity increases with RU for this very gentle fault bend. So the change in dip is only about 10 degrees. And initially you see that this sliding is single periodic with velocities well below seismic speeds. no seismic slip takes place here because they are low RU values. They are associated with large nucleation sizes relative to the dimensions of the velocity weakening region. So they damp or even prevent any kind of frictional instability. And as you increase RU, the main ruptures are firmly in the seismic range. And then as you start increasing them further, these ruptures get more complicated. They're still through-going ruptures, but they are more multi-pulsed here. And then eventually we get to earthquake segmentation, where you start to see partial ruptures. And then as you increase RU further, you get very complex chaotic cycles with one or more partial ruptures between through-going ruptures. So here in this phase diagram, I'm showing the relation between frictional properties and the magnitude of the fault bend. So here on the x-axis, you have RU that's increasing. And in the y-axis, you have the change in fault depth that's increasing from top to from bottom to top. So 0, which means here, these are planar faults. And as you go to these pink bands, they're very, very large, sharp kink bends. So, and we see that rupture style can vary depending both on the magnitude of the fault bend and the frictional properties. So it agrees with previous studies where higher RU numbers promotes earthquake segmentation processes for both planar and non-planar faults. But the value at which faults start to show partial ruptures really depend on the magnitude of the fault bend. So gentle fault bends show segmentation at lower values compared to large fault bends, which show segmentation at much higher values. And this could be because large faults have an overall higher shear stress in the fault and can create these through-going ruptures compared to gentle faults, which have low stress barriers for the same value of RU. So there is, you can see that there's always persistence of seismicity at these fault bends and other structural gradients. So I hope I've convinced you right now that the fault bends and fault shape influences fault behavior. So let's dive into some real world faults with fault bends, like the ones in Nepal Himalayas, where they play a very important role in the seismotectonics of the region. A small introduction to the Himalayan fault architecture. It consists of 3 distinct geological belts, namely the Greater Himalayas, Lesser Himalayas, and the Sub-Himalayas. And all of these consist of sediments that are scraped off from the downgoing Indian lithosphere. And these belts are bounded by forward propagating sequence of thrust faults, namely the main central thrust fault, which is here, and then the main boundary thrust fault, and then the main frontal thrust fault, MFT. And this MFT is the southernmost and youngest fault in the set. And all of these splay faults merge at depth with the main Himalayan thrust fault with MHT that accommodates most of the crustal shortening and intense deformation in this region. Even though there is a general consensus about the fault geometry of MHT with fault bends, there's a lot of debate about how many ramps are present in these in this architecture and what are the dips and dimensions of these ramps. So Gorga earthquake, which happened in 2015, provided an excellent opportunity for us to study the MHT fault geometry. So what we did was we selected 2 n-member fault geometry models and asked the simple question of which fault geometry explains the Gorka's earthquake sequence the best. So for that, we ran a suite of seismic cycle simulations bearing the frictional properties using these 2 n-member geometry models. So the first n-member is from a study published by Elliott. It uses co-seismic geodetic data based on what is known about the fault geometry at depth from geology. So the fault consists of 3 segments. It's a flat ramp system. So first is a shallow 30-degree north tipping ramp between the surface and about 5 kilometers depth. And these are constrained by structural sections, cross sections in the area, following the surface trace of MFT. And second is this flat portion with a shallow angle, finally reaching this steeper mid-crustal ramp. And both co-seismic geodetic data and electrical conductivity study shows this flat décollement with a shallow angle, and seismic reflection profiles also shows the location of the main reflector coinciding with the deep décollement. So it sort of makes sense that a mid-crustal ramp connects this flat décollement under the lesser Himalayas with a deeper décollement under the greater Himalayas or higher Himalayas, which also explains the existence of these of this large anticlinorium called the Gorkha-Papara anticlinorium. The second N-member model is published by Hubbard and her group at Singapore, and it's a geologically informed model of the MHT that is also consistent with seismic observations from Gorkha earthquake. And this study builds a very comprehensive structural cross-section based on kinematic fault-bend-fold model, and it also incorporates surface geology. And this model includes a ramp in the middle of the seismogenic zone, and this middle ramp is required by the stratigraphy exposed in the hanging walls of the MFT and MBT. So like I said, we run a suite of seismic cycle simulations and retain those that best explain the surface slip observations and inferred slip distributions of the Gorkha earthquake. So we have both GNSS and INSAR data. So the top two panels here show two INSAR scenes from ALO satellites, which clearly observe the subsidence of the high Himalayas and uplift at the Kathmandu region. The red line in these panels is the line of sight INSAR displacement from these two scenes, and the black dashed and the solid lines are from my models, and you can see that it agrees quite well. And in these panels, I'm comparing the surface displacement from GNSS data with my models. The red points here are from far-field stations which did not observe much of the surface displacement. That's because the fault slip was buried, and these stations were not close enough to capture it. But the blue points are from near-field GPS stations, and again, there's very general agreement with our models, and especially with the vertical displacement. And the bottom panel here shows the comparison between our models and the inferred slip distributions obtained using these two geometries. Now we can look a little bit closely at the details of the seismic cycle with this geometry. So this is a geometry that does not have the middle ramp. And you can see here the seismogenic zone is fully locked during the interseismic period. All the ruptures, both partial ruptures and the full ruptures, initiate close to the transition between velocity weakening and velocity strengthening, which also happens to be very close to the mid-crustal ramp. So this region is a region of very high interseismic stress buildup, which is what I'm plotting here, the shear stress accumulation on the fault. And so all these red regions you can see are concentrated mainly at the down dip edge of the transition zone. It's constantly loaded and throughout the cycle. And in addition, you also have these previous ruptures that leave behind a notable stress residue that explains the subsequent down dip rupture segmentation due to non-uniform pre-stress along the fault. But what we do not see from this model, this is the Gorkha-like event, is the up-dip aftershocks that was observed after the Gorkha earthquake. This figure here is basically showing you the same information, but the time history of the megathrust behavior using this fault geometry. So here again, I've highlighted the Gorkha-like event in blue. And the super cycles you can see are fairly periodic, and the partial ruptures have very similar size and extent. And the recurrence times of the giant ruptures are between 1,300 and 1,700 years for this model without the middle ramp. So next we can look at the details of the seismic cycle using fault geometry H, and that's the model with the middle ramp in the seismogenic zone. So you can see here this area. So the presence of the middle ramp affects several interconnected aspects of the seismic cycle. So first thing is the middle ramp is able to act as a barrier, stopping ruptures, as in the case of Gorkha-like events, but it is also allowing ruptures to pass through it, creating these larger partial ruptures. And there are also these ramp spanning ruptures that break this region in smaller partial ruptures. So as expected, there's a lot more activity going on with this model. So you have high stress concentration, not only from the down dip edges and previous ruptures, there's also fault bends. The middle ramp area also has persistent seismicity. So whether or not a rupture will pass through a ramp depends not just on the fault bend, because if that's the case, all the ruptures might have been stopped. but it also depends on the previous seismicity and the spatial distribution of stress. So events like 65 and 43, which resemble Gorka earthquake, are stopped by the ramp, whereas 50 and 57 pass through it. And then there are also 59, which happen only at this region. So it's quite interesting that it changes the shear stress evolution by a great amount by just adding one more ramp. And so if you look at the spatio-temporal evolution of slip, there is thrice the variability seen in model H compared to model E. So the recurrence time can change anywhere between 900 and 2000 years. So they are more, supercycles are more aperiodic and chaotic, and partial ruptures are of varying sizes. And also another thing that we notice is that there's variability in hypocenter locations. So ruptures don't necessarily all start from the down dip edge, but you also have multiple initiation points, and all of them are associated with, most of them are associated with fault bends, which we saw were areas of high stress concentration. But the most exciting detail about this model is probably that it was able to reproduce up-dip aftershocks. This is data from Gorka earthquake. So in the 12 hours following the Gorka main shock, there were about seven immediate aftershocks relocated using advanced waveform techniques. And these three highlighted here occurred up-dip of the main shocks, roughly around the same location as the middle ramp. And in our model with the middle ramp, an up-dip aftershock does occur after 14 hours of the main shock. So here I plotted 3 observation points in the middle ramp, A, B, C, and 2 on the flat portion D and E, where the main shock happened. And I plot in these two figures the evolution of peak slip velocity at these observation points during and immediately after the earthquake. So you can see the triggering of aftershocks at the boundary of the post-seismic rupture can be caused by rapid stress changes, but this type of event did not occur with fault geometry E, and these up-dip aftershocks are probably associated with the geometric features like the fault bend. Fault bends are prime regions of aftershock triggering because stress level is already elevated at the start of the main shock. So this is a cool thing. To briefly conclude what we learned so far, what controls earthquake segmentation, both friction and geometry plays an important role, and fault bends impose a very complex footprint on the megathrust seismic cycle. And the role of fault bends in the seismic cycle, we saw that the middle ramp is in the seismogenic zone is essential to consistently explain both post-seismic rupture as well as the early up-dip aftershocks. You can see that there is a lot of complex stress interaction due to these morphological gradients, which also translates to a wider range of rupture sizes and extent. So now that I've spoken about the role of fault bends in short-term seismotectonics, I'd also like to move on to long-term deformation and talk about how fault bends play an important role in the long-term mountain building processes. And in geological timescales, structural evolution of faults and the hanging wall produce fault and fold scarps on the surface, which are then acted upon by environmental and climate agents, which then leads to all sorts of landscape evolution. But fundamentally, all this is driven by tectonic shortening that creates folding and uplift. So we can use these geomorphological features to help us identify the subsurface fault shape and also the kinematics and history of deformation. And one very interesting and important use of long-term geomorphic traces is to estimate fault slip motion. So geologic slip rates at the frontal section of the orogenic wedge can be estimated from abandoned fluvial terraces along rivers using geometric relationships between faulting and folding. And in central Nepal, such geological observations provide a Holocene shortening rate of about 21 plus or minus 1.5 millimeters across the MFT. However, recent geodetic data reveals an average convergence rate of about only 15.5 plus or minus 2 millimeters per year. And this is about 10 to 30% lower than the geologic slip rate. And a lower rate means it reduces the geodetic moment accumulation rate by 10 to 30%. So this can partially resolve and infer discrepancy between geodetic and paleoseismic estimates of moment release. To us, the intriguing question is, if the geodetic rates are indeed smaller, then why is it so? Are we missing something out here? And turns out, folding can cause changes in local slip rates. So this picture taken by Sivan on one of his trips at Fold Scarp at the main boundary thrust near Islamabad, Pakistan, you can see that the folded sedimentary stack here forms an angle with the ramp, and this is called the cutoff angle. And I'm using these cartoons to illustrate the sort of scenario that when stratigraphic layers are at an angle to the fault segment. So they are not parallel, but they're at an angle to the fault segment. And in these cases, the slip magnitude across the fault band changes, leading to slip being either consumed or created, which is denoted by color here. And fault band fold theory provides a simple way to relate this fault shape to fold shape, such that the slip ratio can be defined as a function of the overall geometry. So what we are doing here now is we want to study the megathrust structural evolution along two representative cross sections in central Nepal and East Nepal, with variations in the down dip fault geometry. And these two cross sections basically feature distant degrees of structural complexity. Central Nepal features the famous middle ramp, while the position of the mid-crustal ramp has migrated further south in East Nepal. So what we do here is we use quantitative models of fault band fold theory to study the geometric and kinematic development of faults and create a sequence of structural evolution of the hanging wall as fault slip progresses with shortening. So on the right here is the sequence for central Nepal with the middle ramp. And on the left here is for East Nepal, which with the large mid-crustal ramp. And I'd like to note here that large anticlines like the ones observed in Nepal called the Gorkha Pokora anticlinorium are created due to slip across multiple fault bands like these with the ramp flat ramp geometry. So when stratigraphic layers traverse these fault bands, they are folded and uplifted. And this is how you build topography. So we can now track these changes in fault slip rate across multiple fault bands in the MHT as folding and shortening progresses. So first, I'd like you to look at the ones in yellow here in both the left and right plots. So here, as the rocks start to climb the ramps, folding of the rock layers result in the formation of these kink banks. And this leads to the transportation of inclined beds and slowdowns of long-term fault slip rates at up-dip fault segments compared to the deep loading rate. So with typical Nepal fault structure parameters, you can get about 10 to 25% decrease in the frontal fault slip rates. And during this stage, the rocks are predominantly in a crestal uplift period. So they are raising these rocks while climbing over the different ramps, thereby building topography. Now, as shortening continues, the kink band widens, and eventually this inactive axial surface reaches the top of the ramp. And then the slip rate increases as the back limb are refolded onto the crust. And so this brings the rate back to the deep loading rate now, because the stratigraphic layers are parallel to the underlying fault. So, and the topographic signature of this process sort of now transitions to a crestal broadening stage with just passive transport of all these folded kink bands along the upper detachments. And then in the later stages, folded or inclined stratigraphic layers start to climb these up dip ramps. And this creates a 10 to 25% increase in long-term slip rates across the frontal thrust. So the frontal part of the megathrust can now slip at a rate faster or slower than the deep loading rate at timescales of hundreds of thousands to a few million years. And this process can continue as rocks are continuously uplifted. Additionally, what can happen is that the mid-crustal ramp can break forward, allowing accretion of this Indian lithosphere onto the upper plate, leading to frontal wedge growth. And this process is called tectonic underplating through the development of a duplex system at mid-crustal depths. And this mechanism has been widely accepted as the primary mechanism of crustal accretion and wedge growth in the last 10 to 15 million years. So I'm basically plotting the same information here, but in a much more easier way to read. So you can see the changes in frontal fault slip rates as time and shortening progresses. So the thick black lines here are for central Nepal and the blue lines for East Nepal. And we use 17 millimeters per year as a shortening rate in this model. So in order for, and this light brown block is data from tectonic geomorphology, and this lighter block is all the GNSS velocity range. And so if you want in central Nepal to, for frontal fault slip rates to be in this higher range, 10 to 30% higher than the deep loading rate, then the structural evolution on the flat ramp architecture must be in a stage similar to CN4 or CN5, which means they are bringing up inclined beds up the frontal thrust. So in fact, if you lower this rate also, so if you have a deep loading rate of 13 to 17 millimeters per year, you can get faster frontal fault slip rates of 16.5 to 21.5 millimeters per year. And in East Nepal, it's slightly different. They are well within the GNSS range. So fluvial data provides uplift rates in the order of 8 millimeters per year, which roughly translates to 16 millimeters per year. So the similarity of the deep and the shallow rates can be explained by parallel beds that climb the ramps, creating conditions for more homogeneous long-term slip rates across the orogenic wedge. So the main takeaway is that space geodesy that is most sensitive to deep processes provide a proxy for long-term convergence between the two tectonic plates, whereas measurements that are sensitive to local deformations, such as these geomorphic traces on the surface, capture the kinematics of the orogenic wedge, so which can be slower, comparable, or faster depending on the history of deformation. Now comes a part which is probably the most interesting for this group here, the seismic cycles with slip rate segmentation. So long-term mountain building mechanisms impose heterogeneous long-term loading rates along the MHD fault segment. So we use at every stage of the structural fault evolution, the fault geometry, and in central and East Nepal, fault geometry and frictional properties remain constant. But what we do is we change the orientation of the axial surface that is tied to each fault bend, depending on the orientation of the thrusted sheet, and also the long-term slip rates are also different, obviously. And we simulate super cycles of earthquakes, and these are the different kinds of earthquakes that we're able to simulate. So we have the megathrust spanning full ruptures, which in Nepal it's called giant ruptures, like the 1505 ruptures, and multi-segment large ruptures that may or may not break the surface, like the Great Rupture 1934 Nepal-Bihar earthquake, and the moderate and the partial ruptures that break individual fault segments, like the 2015 and 1833 ruptures in central Nepal. This colored histogram shows how variations in slip rate impact several earthquake cycle characteristics. So here, these are higher frontal fault slip rates, and these are lower ones for central and East Nepal. And you can see that higher frontal fault slip rates produce frequent giant events with less slip per event compared to infrequent but large events associated with slower frontal rates. And the mean recurrence time of giant ruptures also decreases to 1,000 years, whereas for slower ones, it's close to 1,800 to 2,000 years. And the recurrence time of giant ruptures is also more chaotic compared to faster ones that have periodic return times. And long-term slip rate segmentation also impacts the number of partial ruptures between two giant ruptures. And you have twice as many with slower frontal slip rates. And these partial ruptures are of varied magnitude and width, ranging from these multi-segment great ruptures to single segment small ruptures. And you can see that all of these rupture sizes are missing with the faster rates, and which is why you have these frequent large giant ruptures. The recurrence time and and behavior of this region, which is basically very similar to Gorka-like ruptures, these down dip partial ruptures that are bounded by ramps, are surprisingly uniform throughout the earthquake cycle in all stages of the structural evolution. They always nucleate at the transition between velocity strengthening and velocity weakening parts of the fault, and they can have return times of 100 to 500 years. And the general difference between Central and East Nepal, particularly because of the absence of the middle ramp, also has a lot of effects. So you can see that the down dip width of East Nepal is smaller, so it reduces the size of the down dip ruptures. And the range of rupture sizes is also smaller in East Nepal compared to Central Nepal. And so we can sort of conclude that both fault structure and down dip slip rate segmentation determine the seismotectonic attributes of the system. So as conclusion is basically geologic and geodetic rates are compatible, but you can be sure that geodetic rates constitute a better estimate of the deep loading rate, whereas the geomorphic rates reveal the internal dynamics of the orogenic wedge. And how can we link these mountain building processes to short-term seismic cycle processes? We see that there is spatial variability in fault structure between like Central and East Nepal, and there's temporal variability of long-term slip rates, and that induces different patterns of down dip segmentation, which has very strong implications for seismic hazards. Thank you.